Hello, everyone. Welcome to TestFlix 2024. So before we delve into the topic that we have today related to optimizing query performance in big data systems, I would like to give a brief introduction about myself. My name is Sandra John, and I have been working with ZS Associates as a senior performance engineering lead. Let's talk about what are big data systems. So big data systems are basically used to manage and process vast volumes of data, both structured and unstructured. So when we talk about what are structured and unstructured data like which is present in your database, which is already created in a particular fashion, that is your structured data. Whereas PDFs, Excel files, CSVs, zip folders, all of this is unstructured data because they have not been created or being maintained in a particular manner. Where all do big data systems are being used? They're used everywhere approximately nowadays. Finances, healthcare systems, e-commerce platforms, social media, all of these use big data content over there. And big data being present, it requires some sort of optimization. And why are we speaking about query optimization specifically? As I already explained, why do we need it? Let's talk a little bit more about it. So big data systems, they have grown increasingly complex with time. We have huge amounts of data coming from different platforms and in different sizes and formats. So query optimization is extremely important here to manage these volumes more effectively and efficiently. If we talk about at its core, query optimization involves transforming high-level queries into more efficient execution plans. So if I have a query that is trying to bring data from say 10 tables, right? It is definitely going to take a lot more time than it is trying to bring it from a single table. So where things can be broken down into smaller chunks and where things need to be actually executed on a larger scale, that can be identified, and that is where query optimization comes into picture. So with the amount of big data as it grows, the growing need for scalability and distributed architecture systems like Hadoop, Spark, NoSQL databases, they also present their unique challenges which are used here. So from now onwards, we are going to introduce you to the concept of big data query optimization by highlighting the importance of efficient query transformation and optimization in specific areas where it can prove to be performance bottlenecks, considering the modern infrastructure that we are currently using. So what are the key challenges when you're working with big data query processing? Volume, complexity of data, and how frequently the data is coming into the system. Also, the type of data that is coming is quite heterogeneous. That means it is not of the same format. It is not similar across. So it is going to be very different from all the data types. It may not even be an exactly data type, but you have to bring into a correct data type to use it, for which you have to then introduce real-time data ingestions, which is tightly coupled with very complex architectures which makes query optimization even more difficult. These challenges include managing resource contention. All of the resources are getting utilized to its optimal capacity, minimizing data movements from across multiple nodes. We are not moving data continuously across different systems while keeping it at a single system and then processing it over there. And network bottlenecks. These also need to be identified so that they do not add added latency to your already huge data volume. All right. Resource isolation and efficient workload balancing is extremely critical from the perspective that we want data query optimization to happen across big data environments. It should not happen in a very specific area or a very concentrated area, but the workload needs to be balanced so that we do not increase our cost and keep adding servers just because it is getting utilized due to inefficient queries. What are the different techniques for query optimization in big data systems, right? So three critical ones that I think that you can use is indexing, partitioning, and compression. When we talk about indexing, it is to reduce data scans that happen and make it more efficient, identifying the index areas where you can actually put those points to see that the data can be validated over there and checked if those scans are actually needed. Partitioning, by minimizing the volume of data processed by targeting specific data segments. Like if we have a huge amount of data related to customers and sales, if we target specific data related to customers, we'll be able to get more efficient and more qualitative data out of it rather than, doing an overall broad spectrum search. And compression, quite self-explanatory over here. It is to conserve storage space and caching intermediate query results. It improves performance and it is quicker as well, so that you don't need to keep repeating the same computations over and over again. Cost-based query optimizers and caching further enhances query efficiency, particularly in distributed data systems where your data is distributed across multiple areas where you have to bring it together. So if you're doing more caching, what happens is that you're reusing the same data, or you're reusing the same query to get the most frequently used data, and if there has been new data addition to it, it will add to it and then ingest the data further. Let's talk a bit about cost-based query optimization and distributed databases. It is critical for generating efficient query execution plans so that all of the lines of the code or the query that you have written, none of them are performance heavy or are spending a lot on processing that might add to your performance bottleneck. It evaluates different strategies by estimating resource costs such as CPU, memory, and network bandwidth that get used. Systems like Spark, Tez, and Presto use advanced CPU techniques to optimize large-scale distributed queries, balancing factors like network latency, specifically data distributed to minimize resource usage and maximum performance is gained out of it. So cost-based query optimization strategy is extremely important. A mindset to reduce the cost along with your improvising performance is extremely required so that we just don't keep improving performance while running up the cost. This is a case study of Hadoop versus Spark query optimization. Hadoop and Spark employ different query optimization techniques. Hadoop's MapReduce framework is more rule-based. It is more rigid, focusing on reducing data movement and batch processing. Whereas Spark, on the other hand, uses directed acyclic graphs and in-memory processing. This optimizes real-time and makes queries more iterative. Spark's Catalyst Optimizer, it performs logical and physical optimization, making Spark faster, more efficient for real-time data and analysis compared to Hadoop's batch processing. So if you're already using Hadoop systems, maybe you might want to do some POCs and consider if, moving your big data processing from Hadoop to Spark, would it provide you any efficient or added advantages over there? So we spoke a lot about theoretically about how query optimizations need to be done. These are a few practical examples of query optimization and big data systems. First is related to partition, pruning, and Hive. Scanning an entire table, even only when a subset is needed, is one of the problems which many of us might be guilty of doing. We still, search the entire table when only we need to search a subset. So applying proper select queries, where in it, and searching it for a particular either date or a particular subset of data where is deleted might be true or false, using time periods, timelines. These are some things that you need to consider. Broadcast joins in Apache Spark. Expensive data shuffling during joins between large data set is another problem. Broadcasting smaller tables to all nodes to perform joins more locally instead of shuffling like 1 TB or huge amount of transaction tables. Spark broadcasts smaller customer tables to all nodes and joins it locally using commands, and it speeds up the query processing significantly over there. Predicate pushdown in Apache Parquet. Query engines read more data than necessary due to lack of early filtering. So again, one of the examples over here is related to, say, select star, right? If you just need a very small subset of data, you're still using select star everywhere rather than actually, focusing your query on that particular data. This leads to, like, having data and increasing your input output. So what is the optimization that can be done here is to push filters to the storage level, so only relevant data blocks are read. Okay. Next is bucketing and Hive. So Hive follows a bucketing mechanism where shuffling large data set during joins can overload the system. So in the optimization set, what can be done, that bucketing large data sets by columns, it ensures that rows with similar values are in the same bucket, reducing shuffles during joins and hence optimizing your input, output, and network overhead. This is to speak a little bit more in detail practical example of query optimizations related to similar ones: partition pruning, broadcasting and join in Apache Spark, predicate pushdowns, bucketing in Hive, and in-memory caching specifically. Spark jobs that get repeated runs the same transformation on dataset, leading to recomputation and increased input output. So after optimization, what happens if you use cache and persistent Spark stores intermediate result in memory, eliminating the need to recompute transformation in subsequent stages. It eliminates those. And the improvement, it significantly reduces computation time and improved overall workflow performance, especially for iterative queries. So now that we spoke a lot about Spark query optimizations and big data query optimizations, you might have seen a very similar pattern that is happening over here, that we need to be focusing our searches on certain subsets of data. Indexing should be used wherever required and more efficiently, right? Unnecessarily creating joins and using large data sets, all of them together will slow down your performance. So use more of practical examples like these ones and use them in your query optimizations. These will definitely show you improvised query optimizations and results that will help improvise the overall performance and hence bring down the cost of your executions. Talking about the conclusion and future trends, query optimization will remain a critical part of big data applications and usage. As the volume of data keeps growing, we need to keep evaluating where query optimization is exactly required. Future trends include integration of machine learning for dynamic query optimization, advancement in real-time analytics, and use of cloud-based tools for distributed query management. This has already started integrating in multiple systems where real-time analytics is actually being done by a lot of ML based and AI systems, where they are analyzing their entire data set and their query execution time, which queries are actually running up the cost and are taking a lot of time to complete execution, thereby reducing either the number of joins or breaking that query into multiple subsets or subqueries and then rerunning them. As organizations are going to keep adopting more cloud native and real-time data processing, your architecture is going to keep getting complex and even more critical for it gets even more critical for you to focus efforts on query optimization so that this will help maintain scalability and be cost effective in data operations for future needs. That is all that I had for this session, everyone. Thank you for listening so intently. There are multiple ways that query optimizations can be done. These are just a few examples that I have listed down over here. uh, if there are any more that you think, or you have any questions or confusions that you would like to reach out to, do search me up on LinkedIn and you can connect with me there. I'll be happy to answer any questions. Thank you.